Okay. So I'm going to stop the recording. Actually start recording. There we go. So now it's starting the recording. Good. Whew. I think finally they're in business. And let's open this one, bring it over here. Done. Took a while to set it up, and soon we're going to be, I don't know, if they go on a strike, then we can even call for help, but we'll see what happens. So, start of OP345. The very first thing is to understand what we are doing in 345. What we are doing over here is essentially building on your OP244 knowledge and then move towards advanced C++ and all the industry practices that we have. And C++ has evolved, okay? Since C++ 11, many things has been changed, although it is the descendant or an evolved version of C++ 11, but many things has changed since then. It's more natural, it's more flexible, it's more efficient, and we're not only going to talk about C++, but we're going to talk about all the advancements that he had, so we can actually understand how to work with it better. We know that C++, and we talked about the other class too. Surprisingly, the other class went very well. So if this thing doesn't finish, make sure you check the recording of the other class. But C++ works on the same concept of C++ 11, which is object orientation. And it frames all the solutions that it provides around objects. An object is essentially is an instance of a class. If a class, you know all this from OP244, so I'll try to kind of review OP244 concept and fill in the blanks as we are going through all this. So objects are instances of classes. Each class that we have is essentially blueprint of what we want to create. In each class, we have two parts. One is the state of the class, and the other one is the behavior of the class. The state of the classes are the attributes and everything that a class has, and the behavior of the class is what to do with those attributes. So essentially, when we are talking about object orientation, we are actually saying object orientation is to get all that we have for an object, all we need for an object based on an abstraction, and tie it to the behavior that we want. We create a car, we said the car has a speed, and we can build the car with a specific speed as it goes. If we accelerate, the value of the acceleration will be added to the speed, therefore car is going to go faster. And when I show the car is going to show what speed it's going to go with. That's essentially packing the data and behavior together, which is, you have the microphone, so you answer. You have the microphone. If you don't know, you can simply say pass and goes to the next person, which is?
Pass.
Packing the data and behavior together. Putting the data and behavior together. We are talking about three core concepts. The very first concept of object orientation is to put the data and behavior together. That is?
Pass.
Anyone? Encapsulation. That's my hero. So since you answered, the next person is going to be, and then pass it to the lady over there, please. Encapsulation. So encapsulation essentially is packing the data and behavior together. And that's one of the three core concepts of of object orientation. It couples the data with logic. That's the first important thing. If you accelerate a car, that car is going to go faster, no other car. Okay? And your design can either be weak or strong in encapsulation. A weak encapsulation is leaving the door of your house unlocked and get out, which means anybody can just come in. Strong encapsulation is that everything that is private and nobody have access to it unless by you. So we know that everybody has a name, but I have no idea what this gentleman's name is unless I revoke his introduction behavior and ask him to introduce yourself. Hence, he's going to say, my name is Dennis. Dennis. There you go. Everybody? Dennis. Dennis? Everybody. Okay? So now, nobody could tell what the name is. That's strong encapsulation, which means the properties we have are private and they're only accessible. So he could have said John if he decided to. Or if he could simply say, I'm not going to answer. He had decided to introduce himself, therefore he could. We're good with this? That's strong encapsulation. Okay? So, and as you see, the examples go like this. So it's going to be A. I'm going to say over here, encapsulation or classes. Okay? And then the next one. So, an encapsulation is something like this. I have a bank account. It has a balance. And only through the bank account's deposit, withdraw, and display, I can access the balance. I cannot change the balance unless I deposit something into the account, or I cannot reduce the balance unless I withdraw something, and I can only see what it is using the balance. Are we good with this? Are we okay? Are we okay? Okay. Are we okay, everyone? All right. So that's encapsulation, putting the data and behavior together. These things are boring because it's our review of what we've done, and I have to go through it to kind of wake you up. The number of passes we took until we got to encapsulation shows at which state you are. So take this seriously. Okay? All right. Now my lady over there is going to tell me we had encapsulation covered. We have two more core concepts. One of them is inheritance. So inheritance is essentially taking what you had, a design that you had, and sorry about that. We don't have the microphones failed up there. If we had those microphones, I wouldn't pass that around as much. So the microphone failed. It's my backup system, so that's why you're, yeah. Sorry, it's not a very fancy thing, but it works. So people at home, you can hear me, right? I'm not talking to myself, hopefully.
Yes.
All right. And if you see something is happening and you're not hearing something, let me know so I can kind of make it better. Let me see, what do I have in here? May I ask somebody at home to count to 10 for me? Okay, since we didn't hear anything, apparently it didn't work. Again, please.
Okay, I'll do it. 1, 2,
That's perfect.
3.
Stop. Okay, so now I want you to do that again. One more time, now.
1, 2, 3, 4.
Thank you very
5.
much. Fantastic.
Nope.
Much appreciated. Thank you. All right, okay. So the system, the microphones doesn't, that's the microphone that doesn't work, and those are the speakers that don't work. So that's why we're hearing it from here. My apologies. Okay, just wanted to have it in a way so everybody can hear if people at home answer the questions. And soon I'm gonna bring your names up, just be aware. So not only people with microphone over there, but over here, probably I'm gonna say, Julie, please answer. And Julie's gonna say, hello.
The
Hello.
Oh.
All right, good. That's all. So the first name that I saw was Julie. That's why I said Julie. Anyway, so you know the drill, okay? Uh, so inheritance is essentially taking what we already have and adding something to it. So essentially, what we do with inheritance is something like this. We say, I have an animal can speak. Now I have a dog that overrides the speak with a wolf. Okay? So I don't need to create an animal from scratch. Any animal that I create, because the parent spoke, this one can speak too, and therefore I can create a dog and say speak, and the dog's going to say wolf. We're good? Inheritance. Fantastic. And now, Mohammed Sina is going to tell us what is the next feature of object orientation, the course that we were talking about. We talked about, just to remind you, we said, what did we say? We said encapsulation, we said inheritance, and you're going to tell us the last one. Can I give you a hint? Oh, why did you mute yourself? Don't mute yourself. Oh, here we go. Okay, so inheritance, encapsulation, and do you remember? You can say pass.
Pass.
Did you say pass? That was very quiet. Okay, Jill, can you please? Or Gil?
Polymorphism, I think.
Thank you. Yes, thank you. Polymorphism. What polymorphism? And my lady is going to tell me what polymorphism is.
I think something that has like different forms.
Yeah, something that has different. She knows English, not object orientation. Polymorphism is something that has many shapes, which in object orientation means it does what? Do you remember? Pass. Dennis, right? The only person who I know in class. Poor God. Do you remember?
It's being flexible.
Being flexible. What does it mean, being flexible? How can a class be flexible? What does it mean? Polymorphism makes things flexible. Do you remember?
You can use the same name over.
Thank you. So we can call the same, we can use the same name over. Name of what? Do you remember? What can be polymorphic in a class? Functions can be polymorphic in class. So a function, we can have the same function doing the same thing in a different way, right?
Overloading is also a kind of polymorphism.
Pardon me?
Also overloading is a kind of polymorphism.
That's the same thing. Same thing, doing the same different ways. So we have a function, we have the same name, but it has different arguments, right? That's overloading. So doing the same thing in a different way. So from OP244, do you remember the main topics, main categories of polymorphism? It was the last session in your class, last lecture that they covered. They say polymorphism falls into two main categories. Do you remember what they were? No. Close, but no. That's subcategories, the two main categories.
Polymorphism
Yeah, two main categories.
and pass.
Compile time and runtime.
Pardon me?
Compile time and runtime.
No. Close, but no. Polymorphism, we didn't talk about compile time. What? Nah, that's subcategory. The reason that I'm not giving you the answer, I want you to think. That helps you to, because of all this the delay that we have, I'm kind of bring you back to the student mode because you were.
I might know. Runtime and.
No, that's not the one. That's compile time. That's not runtime. We'll talk about that later. Okay, ad hoc and universal. Nobody remembers it, right? Ad hoc and universal. Ad hoc was fake polymorphism. It's a polymer. It's doing the same thing in a different way, but you look at it closely, it's not, like overloading. When you are overloading a function, you call a function add and you pass two integers. You call another function add, you pass two doubles. And you said it's polymorphic because it's the same name but does the work differently. But what compiler does behind the scene is that it attaches the type names to the name. So behind the scene it's add int int and add double double. Therefore it's not polymorphic, two different names. But outside you see, or casting, you call a function that has integer, you pass a double, it casts the double to an integer. That's not polymorphism, it's changing the type. It's the same, it's not two different functions, it's the same function, okay? True polymorphism was inclusion polymorphism, which was virtuals, and templates. When you create a template, you don't even have a function. You just tell to the compiler what type of function I like, and compiler builds it for you at compile time. It's a beautiful thing, right? So, polymorphism, that shows that you need to go lots of review. Do lots and lots of review, my friends. It's extremely important. So polymorphism, an example for the inclusion polymorphism that our friend actually talked about over there, is this. I have an animal. Animal can speak, but the speaking is virtual. Then I have a dog that speaks and says woof, and I have a cat that speaks and says meow. And therefore, when I have two animals, and one of them is dog and cat, when I tell to first animal to speak, because it's a dog, it's going to be a woof. And when I tell to second animal to speak, because it's a cat, it says meow. And when you look at line 24 and 25, there are absolutely no difference with the two functions. The two functions are identical, but one says woof, the other one says meow. Therefore, true, same function doing different things. Capisce? Are we good? Are we okay? All right. Comprende? We're good? All right. So, who has the microphone? I'm going to ask you a trick question. Is animal concrete or abstract? Do you remember?
Abstract.
Oh, sheesh, don't say anything. I'm asking people over here. No, and it's not abstract. Therefore, it's concrete. Why is it concrete? Because you can instantiate an animal. Yes, exactly, exactly. So the animal that I have over here is concrete because I can do this.
Abstract class should be empty.
Abstract? No, it's not empty. Give me 2 seconds.
I mean function.
The function
should be empty.
Yeah,
It
so,
should
so
be
yeah, kind of like
in
that.
other
So,
classes.
yeah, so in here I'm going to put a pointer. I'm going to say a 0, and in here I'm going to say new animal, and this is perfectly fine. Doing something like that, it works absolutely no problem. I can say a 0, and if this one can speak, saying some, right? And then I can, and I will delete it at the end. So that's my schmiggly dingy that I had over there, right? Everything's good? Okay. I save that. And now that I have done this, this program, by the way, has a bug. It has memory leak. Okay? I didn't mention, but this has a bug. It's an example, but with a bug. This program has memory leak. Go find out what it is. Actually, in the other class, I did 2 of them, so we're going to continue like this, so you're going to actually see what the questions in the quiz are going to be. Okay? Why the sample question has memory leak? Why inheritance code has memory leak? This is, so the when we get to the other ones, I'll tell you what the questions are. So this is one of the questions that you're going to get in your quizzes, okay? So, and the concept questions that come through in quizzes always come from lectures. So I'll tell you this is going to be a question. So you better write it down. Not 100%. I came up with 20. One of those 20 is going to be, so this is going to be that. And the answer, go find out. Research why this has memory leak. Okay, so this is concrete because I can do this. So this one, oh, that I'm going to say C polymorph concrete. If I make this one a pure virtual function, then this becomes, so now essentially writing, let me come over here. Now if I make this one 0, then we'll see that these are going bad, okay? Oh, and this is constant. Okay, so as you see now, animal cannot get created. Why? It has a pure virtual function. Okay, therefore this one is an abstract base class. Okay, and this will be an error. Okay. So just remember that. So this is C. Oh, I put C over here. That was supposed to be D. One of the comments I got from one of the students. One of the comments I got from one of the students is that you go too fast. Okay. So the one way to slow me down is to simply say, "Can you repeat that?" Okay, then I know that I'm going too fast. Please, if you see I'm going too fast, can you repeat that? And I'll do it, okay? And I know, and I'm going to go slower. Please do so, okay? So this one is...
The memory leak here was you commented.
Pardon me?
The memory leak was where you commented the line,
No, that wasn't.
where we tried to create animal, no?
That is not the one. Research on it. That's or ask me next time.
Where we can find this announce?
Where can you find? Oh, these code you mean?
Yeah.
Oh, the code's going to be in a repository as soon as I'm finished with the lecture. So essentially, when you go to, so take a look at this just to show you that. So this is A section that we had the lecture just now. You see, it says AA September 8. And when you look at it, this is September 8. And these are all the things that I had over there that we talked about. So you're going to have the exact same thing happening. Every single thing that we do over there is it's going to be in here immediately after the class. Got it? All right. Okay, so let's close all. Modularity is what makes programming easy. Why? Because you create modules to break down a big project into pieces. Especially when we did our programming stuff in OOP 244, we based our modules on classes and classes that are related to each other. So if we had 5 classes in a program, we created 5 modules. And each module has its own what we call translation unit. And that translation unit becomes compiled separately on its own. We'll come to it soon. You'll see. And each module is compiled separately. And the good thing about it is that when you actually recompile your code, when you make a boo-boo or somewhere you debug it, only the module that is changed gets recompiled. The rest remain exactly as what they were. Okay? So that's how modules work. We're going to go deeper in compilation later on. Okay? The building blocks of object-oriented programming are values, objects, variables, references, functions, and types and stuff. We're going to go through them one by one. And classes, members, templates, namespaces, and we're going to go through every single one to exactly see what is the function of each. So values are essentially literal values that you put in your program. Objects are instances of types that you create. So objects usually carry a name, not always. You have variables that are simple objects, usually made up of fundamental types that we're going to go through. References are aliases for already existing names. My name is Fardat, call me Freddy. Freddy becomes my reference, okay? Functions are packages of logic that we name them and we call the name, so the logic is going to be invoked. And types essentially are language's way of specifying what a piece of memory in hardware can represent. So when you say int, in your view, int is essentially a scalar number that goes from minus such to positive such, right? But from compiler's point of view, that integer is tied to 4 bytes in memory somewhere. That its address is a product of 4 multiplied by something. We'll come to it later on when we understand pointers. So I think you get the feeling of what is the difference between 244 and 345 now. We are kind of explaining to you all the things that you have used, hopefully used, how they work, okay? So categories of types. Types are, they fall in 5 categories. We have fundamental types, which are essentially types that come with the language. Integer, character, double, okay? These are sometimes called atomic types. They call it atomic because in physics, long time ago, before quantum mechanics, they thought that atoms are the smallest thing that an object can be, that a material can be broken into. So they call this atomic. So these are, they say these type of things, like when I say over here, I don't even have a type over here, but when I create integer A, you don't break that integer into something smaller. That's what it is, characters. So fundamental types are the smallest types that come with language. Built-in types are wrapper around these things. They still come with language. So built-in types come with the language, but they wrap the fundamental types. When I say wrap, I mean literally wrap. And we're going to use these wrappers. By wrapper, I don't mean Eminem and Drake. I mean wrapper to wrap something around. So essentially, if you have a birthday gift and you put it in a Christmas wrapper gift, that's confusing, right? You're misrepresenting what you have in there. That's what wrappers are. Wrappers in C language, wrapper is an array. An array essentially wraps series of integers in it. Okay? We have pointers. When you say double pointer wraps address of a double into a memory that you can hold pointers in. Things like that. So we're going to go through it and you'll see. So built-in types are essentially types that still come with language, but wraps the fundamental types into things. Then we have user-defined types, which is essentially what we have. We create a structure, we put in an integer, 2 doubles, and a character array, and yada, 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 and other things. So all the built-in types and other user-defined things. So essentially, it's a package of types that we have. Concrete types, you know exactly what they are. We talked about it. Concrete types are types that you can instantiate. Abstract types, they have a hidden representation that only becomes available when they are inherited to something new. You're good? Right? Like the dog. So animal cannot exist unless you create a dog. Then it comes as the nature of a dog being an animal. You good? Abstract, concrete. Abstract, animal, concrete, dog. Dog can get instantiated. Its representation is known, and we know what it does. An animal has unfinished business. We good? All right. We have compilers and type systems that we need to understand. Compilers are essentially programs that turn human language to machine language. So, sorry, C++ is human language, is not a computer language. C++ is human language that we understand. And using that, we convey to the computer what we want to do using a compiler. Therefore, a compiler converts our code into a machine language that CPU can understand and can run. We're good? Language standards are essentially the syntax and the way you phrase things so it's translatable, if that's the word, into machine language. It's the syntax that you follow. It's the standards that you follow, and violating them will cause the compiler to give you an error. And the type system is, again, what we wrap a hardware piece, a hardware resource into a understandable thing for a human being, like calling it double. That double actually represents to 8 bytes. That 6 bytes of it is the poor part, and the other one is the, you know, the scientific notation. Anyways, so we know that from semester 1. So again, it wraps the hardware into what we use. A compiler, when you compile, it has 3 levels of 3 timelines. So when you are developing an application, you have compile time, you have link time, you have execution time. Compile time is when you write and complete your code. You give it to the compiler, and compiler compiles it and converts it to an executable. And understand a machine language. So each module of your application gets translated into machine language. Then linker gets all those things, put them together. That's the second time, link time. Linker puts all these machine languages together and produces an executable. Then you throw everything away, you run the executable, that's the execution time. So if you write print age and you don't define what age is, compiler cannot compile this. That's a compile time error. If you say print and you have a prototype for a print in your module, it compiles fine. It creates the executable. But at link time, if the body of print cannot be found, then linker is going to tell you, I cannot find this function. You promised there's going to be a print. It's not there. That's link time. The last one is, you use that print to print something 5 times, but when you execute, you see it's 4 times. So that's a logical error. Or you thought that you occupied some memory, but you didn't, and you accessed some piece of memory, and it failed, and the program got terminated. That's executable time. Executable time has nothing to do with the compiler. We good? We'll do that in detail at the end of this session. Code segments. We have 4 different places that our code, memory segments. We have 4 different places that our memory is used for. One is code segment, where your instruction for the CPU is going over there. Your for loop, okay? Your if statement. These instructions sit somewhere in memory so a compiler can execute it. This is called code segment. Then you have your data segment, where all your global and static data will sit. After that, you're going to have stack segment, where all your local variables are going to sit. After that, you have heap, which will hold the dynamic memory and stuff that you created. Questions down to this point? Suggestions? Objections? All right. Boring stuff? Don't worry. Soon we're going to have exciting programming things coming up. So, as I mentioned, for data segment, something like integer g is 5, or static instance, these go into data segment. Code segment, we know what it is. Stack segment, when you actually create a function and a local variable, the function and the function call and the local variables you have inside the function go in a stack. Why? Because it comes and goes. It gets destroyed and come back, so those go into the stack. And heap segment is when you create dynamic memory allocation. So that is not even in your executable anymore. It's outside. And it's in the heap. So essentially, this is how your memory looks like. That's the low address memory, so your code goes over there. Then your uninitialized data. Then you have your heap and stack, and it goes upwards and downwards. And at the end, you have your executable, which is command line, arguments, and environment, stuff like that. So so this is how your memory is organized. All right. Talking about building blocks of the language. So we started late, so no break. Sorry, next time come with the coffee. And we're going to start late every single time. The reason is that I have another class in another building 5 minutes before this. So I finished them 10 minutes early. I start you 10 minutes late, so I have 25 minutes to set up. So come with coffee. We don't have break in this class, okay? Unless if you see you're really dying and need to take a break, then let me know. But we don't have time. We have to go through it, so remember that. And today was a perfect example for it. All right. Declarations and definitions. So a declaration essentially introduces something to the program, where definition tells actually how that thing is being applied, being used, and what it does. So declaration introduces a name into the program, and definition gives that name meaning, either local storage or provides logic for the code. So essentially, when you see something like this, integer y line 5 is defining and declaring at the same time. So a definition can do declaration too. In here, when I'm saying integer y10, it not only says that y is an integer, but also makes y available. We'll talk about external later. In here, I'm creating a function called bar. It has function definition, but there is no declaration. If I have a function at the top, it tries to call bar, it cannot, because it's defined but not declared. Declaration is the prototype at line 7. So in here, it's promising that there is a function called foo. So if I compile this code, it will compile just fine. But if I try to execute it, it's going to give me 2 errors. The linker is going to tell me, hey, where is the x you promised? So a prototype for a variable, you know what a prototype for a function is? A prototype for a variable is extern. When you say extern int x, it means there is an integer called x. Trust me. It's going to come. It's in another translation unit. It's in another module. So if in another module you have a global variable called x, your program will run properly, and that is going to be accessed when x is used. But that doesn't define x. It just declares it. We good? We'll come to, you used this before, that extern thingy, in your utils for your project. Okay? Remember that. So, declaration. one definition rule. You can only have one definition for something. You cannot have two. Okay? So you cannot create one function with one name with two different definitions. And that's why you have all the safeguards. Not to confuse because when you create sometimes declarations and definitions come together, you can have many declarations. You can have the prototype of a function in 5 different modules, no problem. But if you have 2 definitions of the function in your executable, then the compiler gets confused which one to call. And because our header files sometimes have declarations and definitions combined, that's why we have safeguards. If not define something, define, and then we write everything so it gets compiled only once. That guarantees that if you have a definition in your header file, it's not going to be repeated. Are we good? Scope is where the name is visible. I want to find a volunteer. Somebody give me their name. Who's gonna? I don't want to put Dennis on spot. What's your name, madam? Rogine. Okay, so we have Rogine over here. Rogine. Okay, Rogine. Okay, so we have Rogine over here. If I say, Rogine, what's the answer to the question? She's going to answer. Why? Because we are in the same scope. But if I have Jane in the next class, class number 10, we are in class number 8. If I say, Jane, what's the answer? She's not here to answer. Unless I say, somebody, go call Jane in room 10 and ask her such and such. So I tell you what the scope is and you go over there. Okay? So scopes are like that. Scopes are where the objects and variables are visible. Are we okay with this? So the scopes that we have block scope. Essentially, any open curly bracket starts a block. Any open curly bracket. And at the beginning of that black bracket, you can start creating variables. At the end of that bracket, that variable is gone. That's a block scope. So block scope, when it's body of a function, becomes function scope. So if you write void foo, parentheses, open curly bracket, you write something, then that block scope is actually a function scope. In any scenario, when you have a nested block, if in any scenario, when you have a nested block, now this could be an if statement inside a function, this could be a method inside a class. Any inner scope, if you repeat and redefine an object or a variable that is in an outer scope, it is possible, but it will shadow it. Okay? So let's first talk about block scope. I'm going to give you an example of the block scope. This is something that you need to know. I didn't say this in the other class. Did I say it? I hope I did. So when you we have block scope. So I is a function scope. It's in a function, right? So I is visible in function main. Then in if statement, I come and inside the parenthesis, the condition of if statement, I say int j equals to yada yada. Then I put a semicolon and add something. This is possible in C++ 17. Doing that makes j available to the entire if statement. And then after that, j is not available. You good? Same thing happens for example, switch statement. I'm saying switch integer j is equal to yada semicolon, then I write j divided by 5. This is just the statement running. It has nothing to do with what is being passed in the switch statement. This extends to the end of the switch statement. So to the end of switch statement, J is a valid thing. You can use it. But when the switch statement is over, at line 23, there is no J. We good? That's C++ 17. It doesn't work in 11, remember. So if you compile, how you compiled your OP244, that's not going to run. It's going to be it's going to be an error. Only C++ 17. And what do I call this? EFG, I'm going to say extending scope variable. So that's an extending scope variable. But if I had int j between line 10 and 11, then it would be only available in the first part of the if statement. Remember that. So if the variable was created, so if I have over here only dies at line 13. Okay? So K dies at line 13. It's only available there. Okay? So are we okay? Do we understand that? J will be right down to here, but K will die over there. Boring stuff, I know, I'm sorry, but these are the things that we have to go through, sadly. Shadowing, we already talked about it. You know exactly what they are. So, so when you create any type of thing, it goes into an outer scope. Anything inner will shadow that and has nothing to do with that value. So I in the first part of an if and I in the second part of if are two separate variables, and they both shadow the I that is outside. What user enters will not be overwritten by the values in here. We good? We okay? I'm essentially preparing you for start writing cool stuff, okay? External linkage, we have already done this. Let me just bring it over here. So I'm gonna, where did I put my cheat sheet stuff? 1 and 2. Copy. So I'm going to add over here a module, existing item. Okay, this module of mine has something in it. So it essentially has a student and has some definition for the student. And then it has a body for a student, whatever that is. Then okay, and then I'm going to bring this for main. So this is going to be my main. Now, as you see at this line, I'm saying if mark is less than minimum pass grade. Do you see any minimum pass grade defined in here? No. So what is that minimum pass grade that I'm actually accessing, getting to that? That's what, forget about line 13. Okay? That is declared in here. I'm saying extern constant int yada yada yada. So it looks like a prototype of the class, the thing. So when you see this, you need to remember that this must be defined somewhere as a global variable. So if I now come to the module, over here I see 2. When you look at the code for module, you cannot distinguish which one is global and which one is file. The global variable over here is the one who has an extern in the header file. And the file scope is the one that doesn't. You can always, now listen to me carefully, you can always enforce for a variable not to become external. I can enforce this thing to be a file scope variable by adding this modifier. If I write static const int over here, it means this cannot be accessed anywhere other than this module, therefore it has a file scope. Static, static can be used for many different things. It has many different meanings. For a global variable to become static converts it to a file scope, which means only this translation unit, this module, can have access to that global variable and nowhere else. When you create a regular variable like that, that has potential to be global if it's externed somewhere. Are we good? Are we okay? So I is function scope. This shadows the I, and this shadows the idea. Are we good? And this is the external one. So this we call external. This is literally called external linkage. So when you have this, or you have a prototype for a function, you have external linkage. When I'm here, this is called internal linkage, which means it forces it to be internal. You cannot make it external anymore. We good? We talked about fundamentals versus built-in types. So fundamental types, int, character, float, double, void, yada, yada. Built-in types are like integer array, reference A, reference integer reference. These are built-in types. Integer reference is just a wrapper around an integer to give an integer a new name. Enumeration and stuff you're going to find out later. I'm not going to talk about it now. They are what we call CV qualifiers. We have, I'm just going to mention their names. You have no usage in OP345, so when the name comes up, you know what it is. When you make something constant, the content of it becomes unmodifiable. You cannot modify it, okay? We have the exact opposite one called volatile. If you make a variable or anything volatile, it is permitted to change. So you're essentially tagging that to be changed outside of your program. Holy schmoly, what does that mean? Let's say you have access to a graphics card. And on the graphics card, there is 4 bytes that they indicate something. That graphics card update that based on location on something somewhere. Then you tag that one as an integer in your program. Although it's an integer, you can put values in it and you can read values in it. But there is some hardware dependency that is changing it without you knowing it. So that graphics card or a network card can change that value without you knowing. That becomes a volatile variable. Volatile thing. We have no usage in 345. That's why I'm not going to go deeper than that. If in future you hear the keyword volatile, know that this means what is volatile may change outside of the logic of your application. And you need to be aware of it. You're going to be very comfortable with this thing when we come to multi-threading. Okay? But for now, just be aware that it exists. Type definitions. In C language, if you recall, so let me save this as GHI, external linkage usage. .cpp. Okay, so if you recall, in C language, if you created something like struct student, if you created something like this, to actually recreate it, to instantiate it, you had to do struct. Look at my student. You had to do this. Remember that in IPC 144? You had to recreate an instance of the student. You had to do this. Why is it giving me an error? I have no idea. Believe me, if you crawl back here, you'll see that it's very distracting. It's .NET. Okay. All right. Okay. So we did that. In C language, they came with a solution for this, not to keep doing this. They say you can create new names for types as you go through this. So, for example, this student, you could have done this like this: student record. Then you could say type def struct student record as student. Then it essentially means struct. So then you didn't need to do that. You could just do this. Now you can actually say student S, because student is this type. You give that type a new name. It becomes very handy. Like, for example, if I have something like unsigned long integer pointer. If you want to have that thing created over and over and over, you know how long it's going to take? So instead of like, and I write over here PTR, it's always easier to take the whole damn thing and write type def unsigned long integer PTR. So instead of that, you can simply say unsigned long integer PTR, PTR2. Makes your life easier and the type shorter. We good down to this point? Also, it has another good side effect, which is if I write over here integer pointer A and B, A, you can say address of val, correct? B, you can't. B is not an integer. B is not a pointer. B is just an integer. Because this is a built-in type, not a fundamental type, the comma over here only affects int, grabs int, not the asterisk. Therefore, integer pointer becomes type of A, and int becomes type of B. So B can be set to val, not the address of val. This is a pointer. This is just an integer. Which is very confusing. I wanted two pointers, for heaven's sake. If that's the case, the solution for it could be a type def. Type def, integer pointer, int ptr. So now if I do this in PTR, P, this could be address of val, and Q could be address of B. They are both pointers because now this is a type of integer pointer. Got it? Lots of information, isn't it? I know, sorry. That's why I asked you to please read it first before you come here. Okay? So this is typedef. And also, there is a new version that, like this all come from C. These come from C. So what did C++ do? C++ version of this will be C++ version says using integer pointer equals to CP int plus plus. How do I write it? IPTR, something like that. So actually, let's do it like this. So I'm gonna say int CPP int PTR will be integer pointer. Okay, so this is the exact, so line number 14 and Terra identical. In C++, you can say, hey, use CPP integer pointer as an integer pointer. And this effect with 10 is the same. That's C++. Those are C. They both work. Are we okay? All right. So ij type def and alias in C++. We already know about namespaces. I'm not going to bore you with all that. So you know what namespaces are and what they do. The only thing that you need to know about namespaces is this. So I'm going to put the example for namespace is that you can actually bring namespaces are to prevent collisions. So when I have, so these, assume these are three files, .h, this is .cpp, and this is main. So when you actually say over here, cout.scope resolution leader, it actually uses that one. You could have said using namespace dot, right? And then don't put the dot scope resolution here. But if you have so many different things that you want to have in here, if you have so many different things, like you're including standard, when I say using namespace std, you know how many things I'm bringing in? Woof. Sometimes you just want to use cout, and you don't want to bring the whole namespace in. That's going to cause lots of conflict. If you want to do something like that, you can always say using dot now when you do something like this, it just brings leader in, which means I don't need to put that, not the entire namespace. So if I write using dot leader, it means only bring that one in, that name in here and introduce it. The rest, it won't get it. So if you want to bring something partially, you can always do that. Okay? It's almost over, don't worry. Two topics and I'm done. First of all, lifetime. Lifetime of things. Lifetime of entities in C++ happen, they live in 4 different stages. Stage number 1, automatic. Any local variable, any block variable is automatic, which means you create it, it dies. There's no problem with it. Okay? These variables come in life when their block starts, and they die when the block is over. We good? The next one are statics, which we're going to talk about later. Static, not the static that we wrote for enforcing file scope. Static as a variable static. If in a function you write a static variable, if in a function, I'm going to cheat and bring it from the other class, because I wrote this over there. We don't have time to write it, so I'm going to write it over here. So if you have a local variable and you make it static, the lifetime of the variable becomes global, which means it will get created the first time the function it calls is called and stays alive thereafter. Which means if I call fa first, it comes over here, line 12 happens, s is created and set to 1, initialized to 1. Then I add to s, it becomes 2. Then I print it, 2 is printed, right? Then I get out. Fa is called again. It comes in here. Because the static variable was created, line number 12 is ignored. S exists and it has 2 in it. Becomes 3 and 3 is printed. Okay? And that's another question for your quiz. Static variable in a function. How to enforce a file scope using static? That's another question for the quiz. So I'm going to ask you, create a file scope variable for this thing to how can I make this global variable to have internal linkage to become file scope? That's static. Oh, and a student over there asked me, what is the difference between typedef and define? Can I just define integer pointer like we did in C, define int ptr to ptr, int asterisk to ptr, and replace it for me? And I answered, that's happening at pre-compile time, not even compile time, which means define is literally a search and replace. It's as if you misspelled something, you search for it, and you say, replace everything that I spelled like this, like that. So you literally search and replace before compilation. Define is that. It has nothing to do with C language. Anything you start with a hashtag is not C++ or C language. It is C++ compiler language. You are telling the compiler to perform actions before beginning to compile, before starting to compile. Okay? So remember, all the things you write hashtag in front, you are telling to the compiler, do this before you compile. And that's the difference for it. So this one will be statics, JKL.
Excuse me.
Yes.
Would you please repeat the question you said that we have in quiz regarding this static keyboard? Like,
yeah, if you recall, I mentioned over here when you create in here, it was internal linkage. Where did I do that in? Oh, it was in module. So I said when you add a static to the global variable, it makes that a file scope. It forces that variable to be file scope. This variable cannot be linked externally anymore. It forces it to be internal. That's the question for the quiz.
oh, okay, thank you.
All right. That wakes people up. Okay, so that's that. Yes, automatic. The static ones are like that. Dynamic one, you know what it is? You know to use new, which means the variable gets created when new is happening and it dies when it's deleted. And heap, it's all in your hands. And at the end, we have another type called thread scope, which you'll have no idea. I'll talk about it at the end of the semester. Okay, just remember there's a fourth one called thread scope. Essentially, in future, I'll teach you to write one function and execute that function 4 times simultaneously. So they all run in parallel. That's called multitasking or multi-threading. So that's another scope that we talk about when the time comes. It's called thread local. We'll find out later. At the end, we are going to talk about compilers and understand what compilers are. And where did I put my teaching notes? That's not the one. Sandbox and today's lecture, compiler and execution. So compiler process happens in 3 stages. Compilation process happens in 3 stages: pre-compilation, compilation, linkage. Pre-compilation are all the hashtags being resolved. So the compiler keeps going through the hashtags and expands them until no hashtag is remaining. That's why I brought this example, the boo-boo and hee-haw example. What is the boo-boo and hee-haw example? I'll show it to you in 2 seconds. So copy. Now in here, I'm going to add a couple of things.
Get away.
Add existing item. So boo-boo. Oh, I have them both here? Oh, this. Sorry, wrong place. Notes, section B, here. There we go. So boo-boo and hee-haw. What are boo-boo and hee-haw? And I have another one over here. Okay, so let me remove. I'm going to remove it anyways afterwards. So boo-boo is half a program. You see that? I'm writing include, namespace, main, and I stop. Right? Then I write the second program. It's the rest of that in a completely separate file with a stupid name and a stupid extension. Right? Now, I'm going to remove these completely from my project as if they don't exist. So I'm going to remove this from my project. And instead, all I need to do over here is to do this. I'm going to go in my main, and I say include boo-boo, include hee-hee. That's it. That's my program. Now, if I run this program, it actually compiles and runs and tells me yada yada. Oh, it's not Sep06. I have to fix it. Anyways, you saw what happened. So include is nothing but copy and paste. Don't think you are doing some magical library adding thingy. All the include does is that in a header file, they added some declarations. You're just copying and pasting those declarations into your code. That is why I always scream at the top of my lungs, do not do just in case includes. Write an include statement only if you really need it, because it's going to bloat the source code of your application. 2 includes over here, it looks 2 lines, but each one is actually including 4 lines. So before the compilation happens, it's going to be 4 lines that it's going to get compiled, or 5. Now imagine you include standard input output header file, or include IO stream for no reason, or include F stream for no reason, or include vector for no reason. You do that, it's going to include lots of declarations and definitions that you don't need. Don't do it until you need it. My way of doing it is that I write the code. If it gives me an error, I'll add the include. Okay? So don't include it until you really, really need it. Whoever is talking at home, please mute your microphone if you're not talking to me, because I hear you telling a story to someone that I'm not interested in. Thank you. Let me see, who's it? Somebody's talking over there. Okay. Anyways, so that's that. So first that precompile, then compilation begins. And we have already talked about that, and I'm going to actually show it to you like this. It's actually much quicker and easier. Copy. Existing item. So when you write a program, this is what you usually do. You have several modules. Each module, 1, 2, 3, 4, 1.cpp, 2.cpp, 3.cpp, and 4.cpp. These are 4 translation units, 4 modules. When you compile the code, first the includes and the defines and the if define, if not define, end ifs, all the things that start with hashtag gets expanded until none is left. Then compilation begins. So first precompile. Then 1.cpp gets compiled, if successful, object file. Then 2, then 3, then 4. If all of those are good, then I have 4 object files. That's when compilation ends. Then linkage happens, which puts those object files together and gives you one executable. If you have a syntax mistake, you get a compiler error. If you promise something exists, like you have a prototype for a function, but you forget to add its CPP file, then it tells you function not found. That's linker. Execution problem is when you don't occupy enough memory in RAM and you use it and it fails on you. Or you wanted to print something 5 times, you print 6 times by mistake. That's logical and incorrect resource management. And those are the stages of compilation. Now, how the compiler works and what are the commands lines and stuff, please go read it. Well, I'm not going to tell you, right, G++-O, please go read it. They're all in the notes. Okay? Questions? Suggestions? Objections? I think that's it. Now, I asked one question in the other class. I'm going to ask one question over here. Having all the problem that we had at the beginning of the class, this is the question that I'm going to ask. I'm going to ask this probably a few more times as we are going through the session. And people at home, please respond to this in your chat if you don't mind. Okay, so in your chat, respond to this, and that actually shows me how many people are actually listening. So, scale of 1 to 10. Scale of 1 to 10. How much did you get and understood from the session? And be completely honest. You can give me 0, I don't care. I really need to know. Okay? 1 to 10. Give me a number.
Like an 8.
8? 8? Don't repeat. Think. 7? 7? 9. Okay.
7.
The other class I was at 4 and 5, and we didn't have any problem. Either you're lying to me or you're shy to say that it was. Okay, please think about it next time and be honest. That's completely unrealistic outcome. The average was 8. That never happens. If I'm a 6, that's a beautiful day in my life. because students never learn an 8 in class. Absolutely lie. Okay? Next time, please answer honestly. Okay, now number 2, curve of forgetting. I mentioned the other class. Did they mention it in 244 and IPC? Anyone? They said no. Did they tell you what curve of forgetting is? Huge research is done long time ago. How to commit stuff to long-term memory. When you receive a lecture, the same day of the lecture, review it for 20 minutes. A week after, 1 week later, review it for 10 minutes. 1 month later, review it for 5 minutes. And it's gonna get committed to your long-term memory. Guaranteed. Okay? So now, because our lecture is more than, this was based on an hour. Because our lecture goes 1 hour and 30 minutes approximately, make that 20 minutes 30, make that 10 minutes 15, and make that 5 minutes 10. Okay? It's a little skip. For 1 hour lecture, that was 20, 10, 5. So for this one, make it approximately. So if you have 3 classes in a day, that means you have an hour and a half of studying to do that day. If you want to be an A+ student. Did I get through to you? Okay. Please have yourself a beautiful day. If you see me going too fast, could you please say, repeat that again? Okay, so I slow down. Have a good one. Let me stop this, and then I'll answer your question. I'm a very bad person in multitasking. And also, all the stuff that I have written in class right now, I am sending it right over GitHub. So it's going to be up there in 3 seconds. Let me just put it up. Give me a second. Okay, I'm yours. What's up?